Hi, I'm Xuanyu Wang. I'm an assistant professor at Xi'an Jiaotong University. I'm glad to share our paper, CollabVisAdapt Spatial-Temporal Context-Aware Adaptation of Shared Object Visualization for MR Telecollaboration. This work was done with my colleagues Wang, Weizhan Zhang, Shuaichen Caixia Yan, Shuming Yang, Haipeng Du from the university, and Wangdu Chen and Qi Wang from MIGU Video. MR Telecollaboration allows a user to work on a local physical object with remote users' avatars as if they were co-present in the space. One of the most critical challenges in telecollaboration is that, unlike face-to-face collaboration, the shared object is not physically available to remote users. It is thus expected to provide remote users a virtual replica of the object that is freely manipulatable and view-dependent, which is high spatiality, and of high visual fidelity, and generated and dynamically updated in real time, which is high real-time performance. To simultaneously optimize the visualization in these three aspects, existing methods leverage volumetric capturing and reconstruction via specifically designed pipelines. However, they mandate substantial hardware resources and are thus too costly and complex for mobile and everyday scenarios. Other solutions employ sparse RGBD cameras and point cloud-based rendering. They offer a certain level of spatiality, but often suffer from rather lower fidelity compared to conventional 2D video-based solutions. Nerve and 3D Gaussian splatting support photorealistic 3D reconstruction. However, the time-consuming training process, even significantly accelerated, remains prohibitive for real-time high-fidelity reconstruction of dynamic objects. Furthermore, objects with complex textures on planar surfaces, such as writings on boards or papers, screen contents circuit boards, are very common in everyday collaboration, and they do not require 3D modalities. While the aforementioned visualization modalities cannot simultaneously optimize SFR when singly employed in mobile setups, researchers explore mixing multiple modalities to complement each other. They combine mesh and 360 video to balance spatial perception and fidelity, or integrate nerve with point clouds to handle both static and dynamic objects. However, the predefined rigid modality function mappings limit accommodating flexible switching across modalities, as user preferences for modalities could differ regarding collaboration contexts, and manual switching could increase cognitive load and disrupt collaboration continuity. Similar autonomous switching techniques exist in 3D UI studies, where researchers explore adaptation of UI components based on user-centered contexts such as interaction semantics, head rotation, and eye gaze to improve task efficiency and reduce cognitive load. Therefore, informed by this strain of research, we explore applying such adaptation to shared object visualization in tight collaboration. Next, I will introduce how we explore the adaptation of visualization modalities based on spatial context and temporal context, and present the implementation of the CollabVisAdapt proof of concept prototype and the user evaluation based on it. Observing that users constantly adjust viewing distance to interact with the object for task phase-specific demands, such as detail checking and overview inspection, we couple viewing distance and task type as the spatial context. This leads to our first question. How does spatial context affect user prioritization across the SFR visualization dimensions, and how to computationally adapt modalities accordingly? We conduct study one to answer this question. This study, participants assume the role of remote VR user and complete inspection tasks in four viewing distances. They complete proximal detail examination tasks focusing on text and patterns at the first two distances, and complete distal overall observation tasks focusing on shape and structure at the last two distances. In each trial, there are three visualization modality conditions, which is the view-dependent video frames, 3D Gaussian splatting, and mesh. VDVF caches video frames captured by the local user's camera and the corresponding camera viewing angles, and presents the remote user the frame with the closest capturing angle to the remote user's current viewing angle. This modality presents a certain level of S since it supports freely adjusting viewing angle and achieves high F and R. Mesh is produced by generative approaches from a single image within a few seconds. This modality could be feasible with high S and medium F and R. With more input views, 3D GIS significantly outperforms other methods in photorealism with high S, relatively high F, and very low R. We record task completion time, accuracy, and users' perceived optimal observation distance for the preferred modality considering task load and visual comfort. And results show that users prioritize fidelity in proximal context and prioritize spatiality in distal context, adaptively employing VDVF and 3D GIS or mesh modalities in the corresponding spatial context is necessary. We also identify the modality switching threshold through psychometric function fitting, which provides a quantitative foundation for the adaptation. In addition to spatial context, we need to further address modality adaptation according to temporal context. The generation of 3D modalities incurs inevitable and variable latency, leading to situations where some modalities, although being the most preferred in the current spatial context, are not yet accessible. This thus leads to our second question: how to adapt visualization modality with the existence of generation delays to facilitate collaboration. We conduct study 2 to answer this question. The scenario is still planar observation. Participants complete distal tasks in the optimal viewing distance obtained from study 1. In each trial, there are 4 switching schemes considering different combinations of modalities. To flatten the curve in the R dimension and avoid keeping users waiting too long for a 3D modality, we introduce a new mesh F, which is a fast mesh modality, and the previous mesh condition is renamed as mesh S. Results show that SS4 is the optimal temporal modality switching scheme, and it balances the F and R dimensions and allows gradual refinement in the S and F dimensions. It makes the overall workflow more efficient, smoother, and more reasonable. Next, I will introduce the CollabVisAdapt prototype and evaluation. There are 3 main components in the prototype implementation. The Telecollaboration component supports basic user avatar interactions, object framing, hand collision detection, and the hybrid visualization component implements and maintains all the modalities, and the modality adaptation component switches between modalities based on spatial temporal context. Based on the CollabVisAdapt prototype, we conduct a user study to evaluate the effectiveness and usability of our adaptive visualization mechanism. The study scenario is a real-world remote support printer repairing session. Participants act the VR user's role to lead the task, and they move and communicate naturally to complete tasks as in real-world scenarios. We compare our adaptive visualization with the manual switching condition and record task completion time, asset task load, overall preference metrics. Results show that compared to manual switching, adaptive visualization enables smoother completion of telecollaboration tasks with less effort and leads to reduced completion time and communication costs. It syncs well with the user's viewing intentions and motions, intuitively providing the most contextually appropriate modality. We have also demonstrated the system's application in collaborative flower arranging and computer assembling scenarios, which is detailed in the paper and supplemental video. In conclusion, we have explored the adaptation of shared object visualization based on spatial temporal context in MR Telecollaboration with a mobile and easy-to-access setup. We have investigated the user-preferred SFR characteristics of visualization modalities through 2 user studies and have developed the CollabVisAdapt prototype based on the user study results. The evaluation has validated the effectiveness of the system. Future work can be done from reducing generation time and enabling automatic calibration, exploring collaborating on large scale and multiple objects, and in multi-user scenarios and dynamic tasks. Thanks for listening.